All right, here we are, the end of the road. If you didn't notice, I sent out an announcement about it. There is another survey, just like the survey for test one. It's the exact same, adjusted for test two. So basically, I do ask again the same question of, hey, have you taken physics before? Because if y'all remember the last time I gave you all the survey, I complained that that Canvas's web course is annoying and the new quizzes has less functionality than the old quizzes and yada yada yada. Long story short, the reason I asked that question is I very much want to look after the fact, and I want to look at I want to look as a class and see how much does taking physics in the past matter. Not because it changes anything. People can't go back and take physics in high school at this point. But because in future classes it gives a good, hey, if you've taken physics before, this very likely will be easier for you. If you haven't, it's going to be more challenging, but that doesn't mean impossible. And then I can look at and I can show grades and say, like, look, if you haven't taken it, people are still very successful, yada, yada, all those kind of things. So all this data I collect is ultimately to support future students and kind of just, it's good to know what you're getting into. That's kind of a rule of thumb. It's good to know if I fit into this category with this much prep, maybe here's how much work I have to put into things to be successful. So if I can provide people that information, yay. That's great. Okay, we are not on fixed axis rotation. That was not the one I was looking for. So we are finishing up moment of inertia and angular momentum. So remember, the punchline is that everything in rotation has a linear equivalent. And so to that end, what we spent a lot of time on last class was and we have mass, great. And rotation, we have this thing called moment of inertia, which is I, and y'all did a lab. And I think the lab was at least successful in you all understanding that the farther the mass is away, the harder it is to spin the object. The farther away mass is, the harder it is to spin the object. And as I was thinking about it, and as I was working with you all, it's actually very easy to explain why this is. So if I take a meter stick and I spin it in a circle. So if I spin this meter stick in a circle, it's all rotating. It all makes one revolution. So the angular velocity is the same, all that jazz. But if you look at a point really close to it, it makes a really small distance. If you look really close, it makes a really tiny circle. Whereas if you look on the outside, it makes a giant big circle. Like it has to travel really far. It's hard to make things travel really far. So that's why moment of inertia is what it is. It's hard to make things travel a farther distance. Like that's the idea. So great. We gave you all the equation. It was the sum of mr squared, which ends up being r squared dm. And then I gave you a bunch of shapes, and I said, look, if we had calculus 3, we could actually derive these, but I'll give them to you if you need them. So a sphere was kind of the best. If you rotate about the center, a sphere had the lowest center. I say the best. A sphere had the lowest center mass, and a hoop about the center, like a hula hoop rolling, had the highest center mass. I do want to clarify, I mentioned this during my lecture class. Lower moment of inertia is not better. Higher moment of inertia is not better. There's not like a better or worse. It's all based. So with you all mostly being engineering and things like that, this is a really important thing for you all to realize. It depends on the application. It depends on the application on what you want. Sometimes you want something that'll kind of take a bit to kind of get up to speed. Because the opposite's also true. If you have something with a high moment of inertia, it's going to stay rotating much easier. So if you have like a flywheel and you want to store energy rotationally, you want something with a high moment of inertia because it's going to store that energy better. It's going to store more energy for the same rotation. So if you want something that spins up really quickly, then a sphere is going to be better for you. And then you also get into how you're going to attach that sphere to something, and that might actually be trickier than a cylinder versus all that stuff. So these are the kind of questions that engineers have to answer versus physicists. Like I teach you all the basic concepts, but what you all have to decide, it's not just, hey, I need to understand the physics. It's you got to understand it within a real world context based on the deliverable. What product are you trying to make? And what product meets those requirements based on manufacturing requirements and materials and all sorts of things like that. And that's where it gets really interesting. That's where engineering, that's the fun part of engineering. And the really interesting part is you need to not only know the physics, you also need to understand manufacturing. One of the best things you all can do in manufacturing is get connected with the people that actually build the parts. It's one of those things that you'll kind of hear. So as engineers, you design a part, but if you've ever like done anything in a car and you've ever changed an oil, you realize not all cars are created equal as far as how easy an oil change is. And that's because the engineers sometimes don't talk to the people that put it together. And they're like, oh, here's a spot, I'm going to put this here. And then the mechanics who are actually doing the work say, yeah, that's awful. Like, how the heck am I going to get to that part? I have to take like 5 things off. So good engineers consider those things as well. Keep that in mind. Random things, but fun things. Anyway, then we did parallel axis theorem. It's super, super nice. So instead of having to do an integral, if you already know the moment of inertia, you just shift it. So we did this problem, and this is kind of an easy way to remind you all this. You take an object with a known moment of inertia, you shift the axis parallel, an axis that's parallel, you shift it, and the new moment of inertia is just the original plus the new plus md squared, where d is the distance it shifts. I'm going to leave this up for 5 seconds because literally the next question I'm going to show you is do it. So kind of check this out. See if this makes sense. We did this question last class, but remind yourself of it. So this sphere, the axis of rotation is shifted by r. So we just added mr squared to the OG moment of inertia. And we got the new moment of inertia. And it was great. Okay. All right. Try this one. Using the parallel axis theorem, what is the moment of inertia about a rod of mass m about the axis shown below? I'll make that picture a bit bigger, just easier to see. The moment of inertia for a thin rod about the center is 1/12. So, and in that case, I'm saying it's spinning like my meter stick here. It's spinning. If you spun a thin rod like my meter stick about the dead center, its moment of inertia is 1/12 ml squared. L here is not the radius of it, it's the entire length of the rod. All right, great. Find the new moment of inertia.
Wait, L is the length?
L is the length of the rod. Yeah, so instead of using R, we use L here because it's just it's a little bit more convenient than radius, like the rod. You could convert it to the radius if you wanted to. Try it out. I'll go around and, trust me, draw a picture. Draw a picture with the original moment, the original axis, the new one. Go from there. That's what I'm going to be creeping on your papers for, to see if you're making sense of it. And then we're going to do this exact same problem, but we're going to integrate to find the answer. You're going to see why parallel axis theorem is so nice for us. Remember, y'all, do it just like the last problem. Find the original axis of rotation. Find how much it shifts by. That's where a picture is going to help you. If you don't draw it, you're going to make a very high chance of making a mistake.
Yeah.
Nice. Yeah. All right. So then we just got to figure out what the shift by. Right. Of the original one. Yep. Yep. And so what equation are we going to use if we kind of shift it over?
You have it in the 1/12 ml squared. Dimensional. How much it is?
So where's our original axis rotation? The original is 360. We kind of put that in the picture, then you can kind of show in the picture how much it shifts the left, and that'll make it easier to kind of talk about it. So again, the power of a picture, y'all. Literally, so what I'm going to do is just draw where the original was. Where was the original? Dead center. So I just draw that. If you do not draw this, you're making your brain work harder. There's my original moment, my original axis. Took me 5 seconds. Like, drawing this picture takes about 5 seconds. And it saves you so much time. It saves you so much brain power. So remember, y'all, the equation that we're going to use is the same one we used last time. We take the original moment of inertia plus md squared, where d is how much I shifted my axis. So that's really all you got to determine. How much did my axis shift? And again, if you try to do it in your head, you can, but you're going to be way more likely to make a mistake. One day you'll believe, if you don't believe me on that yet, one day you will. Trying to do it in your head is not actually a useful practice to do. It actually gets you in bad habits. Every time I try to do something in my head, I have a very high chance of it. Every time you all see me do like a mistake up here, it's because I did stuff in my head too quickly. No, that's fine, but you just write out the math. Yeah, but it's some math, yes, like 3 times 6. That's acceptable.
No, I can do. No, it's just energy.
Oh, that's you can't. But
108.
36 times 30.
36 times 30.
Oh, yeah.
I
got 30. Don't worry, I'm with you. No, so the moment of inertia for a thin rod about its center is 112. We're no longer rotating around the center. Yeah, so we're finding the new one. Yeah, so I give you I naught. So I give you I naught, the OG, the one that we referenced, and then we're going to shift it to the left side of it, which means our distance is R. In this case, our distance is not R, and the question is what is it? Okay. So, next step, just to draw this on the picture. This is the distance, but you need to put that in terms of L. Oh, and the final, I'll give you all the final answer. Gosh, it's something, I think it's like 7/12 or something. 736, yep. Just, you all can do this. It's just, can you figure out what this D is? So our givens, I give you the OG moment of inertia, 1/12 ml squared. We're solving for the new moment of inertia. How do we do that? Parallel line theory. If you know the moment of inertia about some axis and you shift it, this awesome equation gives you the new one without having to do any algebra. Or sorry, any calculus. You have to do algebra. Without any calculus. Without any integration. And you just have to figure out what that D is in terms of L. If you can do that, the rest is cake. And the picture, give... Alright, did y'all figure out what the distance is shifts is? Yeah, it would just 2 6. Yeah, 2 6L works is fine. Yep, same thing. Good. Cool. Were you all able to see that as well? The 2 6 or the 1/3. The question is, where's my axis start? If you had to describe the original axis, where would you say it's at? Do you all figure out how much it shifts? That's really the, once you figure that out, just plug it and check it. So, all right, so to figure out how much it shifts, you got to figure out where you started. You got to figure out where you started. We did not start at 0. Where did my axis start? The middle, 3L over 6. If you really want, you can do L over 2. You could either do L over 2, but you could also do 3L over 6. You're going to see why I put it 3L over 6. It's a bit more convenient to work with. If this is 3L over 6, what is my distance that I move? 2L over 6. So again, this is the only challenge to this problem is figuring out how much I shift the axis. And the picture helps you kind of see that. It starts at 3L over 6. Axis rotation, how much does it move? What's that D on there? 2L over 6. And the last step, y'all, is just plugging that in. So we have 1/12. That's my original. Plus M times 2L over 6 squared. And it's just algebra at that point. So you get I equals, and I'm going to give myself more room than less. I equals 1/12 ML squared plus 4L over 36. 4L squared, there's an M in there too. And then least common denominator, 1 over 12 becomes 3 over 36. 3 over 36 plus 4 over 36 becomes 7 over 36. When it comes to moment of inertia calculations, y'all, this is going to sound rough, but this is as easy as it gets. And I don't say that to be like, if you didn't get this, shame on you. No. That's not the purpose of that statement. That statement is to show you that parallel axis theorem is awesome. I'm about to show you all how much worse it gets when you actually have to integrate it. It's not the worst thing in the world, but it's definitely not as easy. Just adding MD squared is really simple. You just got to figure out the distance. You add it. It's all algebra. We are going to enter into the world of calculus, and we're going to do this exact same problem, but with the definition of moment of inertia and using a trick for actually, like, we got to do an integral. We're going to do the integral of r squared dm. But before we do that, I need to recognize your presence. Did you want me to do the joke? Oh, yeah, go for it while they're doing that.
Okay, I got the joke while we were waiting, and it's called, wait, did we do this one?
No, that one's pretty good.
Okay. I tried calling the tinnitus helpline, but there was no answer. It just kept on ringing. Yeah. Okay, I'll get the sheet, and if you need it, just let me know.
It's good. No, it's great. They're all great. I called the tinnitus helpline. There was no answer. It just kept ringing. Tinnitus is when you have permanent ear damage.
Tonight.
Yeah.
So it's like tonight is.
No.
What is that? Okay.
It's the thing that lots of high schoolers get.
Yeah.
People get when they're younger because they don't take care of their ears, and then they suffer for the rest of their life.
They have like the mandatory fire drills once a month. And it's
Yeah, but that's not. Yeah, those aren't large enough. usually the most common reason people damage their ears is they've gone to too many concerts, or they mainly listen to music with their headphones too loud. It's amazing what blasting lots of energy at your eardrums does to it consistently.
Yeah, my mother did that. She warned me all the time. She's like, "Don't damage your ears."
Yep. Oh yeah.
Because she used to go to tons of rock and roll concerts. She worked for AC/DC.
Yep.
When she was like younger, she's like, "Don't do it. No, I can't hear anything."
Yep. Well, and you can always hearing protection is a thing. Yeah, it's just one of those. Don't touch the stove. Some people are gonna still touch the stove. Most kids are. The you know.
I think
It's all a part of growing up, right?
a good portion of the population.
All right. If y'all need Leo, he exists. Oh, did you miss it? Oh no, just tell Leo and he can update it in here. All right. So we had so much fun doing this with this way, which is the nice way. Maybe I should have started with the worst way to sell it to you. Okay. So this is our integral we need to do. I equals the integral of r squared dm. If you all remember, there's an integral that looks very similar to this that you all did recently. It was in preparation for the last test. If you all remember, we did the center of mass, had 1 over the integral of dm, and then the other thing it had was r dm. Man, those things sure look similar. And we had a trick for doing this integral. There was a trick for doing this integral, and it was basically, we know the mass is going to change based on where you're located. We got to integrate it all, so we're not integrating with respect to r currently, but r changes. So what do we do with that dm? If only there was a variable that related location to density. I give you away, but I'm pretending like no one does. So we just make it a one-dimensional density, and we replace mass with dm. We replace length with dl. And this little signal, this is lambda. Lambda is used for many things. Wavelength is one of them. In this case, we're using it for one-dimensional density. Previously, you all saw me do it this way, and it's fine. This is fine as well. And ta-da! Look, now we can integrate. We replace dm with dm with rho dl. We pull out the density. We replace the dm with the dr. And now you can actually integrate the function. How nice. R squared dr. Because remember, y'all, r was not a constant. You can't just pull r out of the integral. You can't say, oh, I'm integrating dm, therefore r is a constant, I can pull it out. No. And you're going to see that with many more equations in your years to come. You have to change variables to actually be able to integrate things. Unfortunately, we don't get to practice that in this class as much as I'd actually like to. This is a skill that takes a lot of time to develop. You've learned how to use calculus, but learning how to do integrals and how to actually set up the integral is a skill that takes a good amount of time. In Physics 2, you are going to learn the following integral. The electric field, don't worry about this one right now. This is just a Physics 2 future problem. K dq over r squared, where q is charge and r is the distance away and k is a constant. K is a constant, yes. R will not be a constant, so you will have to change q and do something that can be integrated. And you know what's nice? It ends up being that dq is just going to end up being lambda dr, where lambda is instead the charge density. Instead of a mass density, you'll have a charge density. So it's the same trick. It gets worse, though, because this is a vector. Breaking into x and y components. Yay!
We never even did anything like
No, you often will. You may not even see that. It depends upon your Physics 2 professor. It's a skill that takes a good amount of time, and there's so much stuff you have to cover in Physics 2 that you often might not see it. But
you still taught us the derivation.
yeah, I want to mention it to you all just in case.
We lost a lot of weeks of the hurricane this year.
All right, go. So here's this problem. Find the moment of inertia of this rod. Nothing's given. Yeah, so it's good. So I'm going to work through this one with you. I'm not going to just say do it right now because I can almost guarantee it's not going to make any sense. What's given? There is only one thing given in this. Okay, I guess there's two things given. You have to know where you're starting from. You have to know where your origin is, where r is being measured with respect to. It's the axis. So this is my axis. That's important. I can't really write that in a list of givens. So I'm actually going to jump kind of to step 2 because step 1 is going to be more confusing than it's worth to try to like explain what would go there. So step 2, what are we finding? I. How are we going to find I? We are going to integrate r squared dm. And I just told you all that this integral as written is not very useful for us. You got to do one extra step, which is it's going to be the integral of r squared lambda dr. Remember we replaced that dm with the density times its location. Density is mass over location, so we just make that swap. Okay. So then what I'm going to tell you, we can pull lambda out, and you may be like, we don't have lambda. Don't worry about that for now. That's a future problem. Trust me, I'm not going to need it.
Okay.
So for now, just trust me. Pull it out. We'll worry about it in the future. We're going to integrate r squared dr, where r is the distance from the origin. R is the distance from the origin, the axis of rotation. So my question to you all now that I've just written the equation, I haven't done anything crazy, I've just said this is the equation for finding the moment of inertia for a one-dimensional object. What are the bounds of that integral? This is a definite integral. Your rod doesn't go to infinity. It has bounds to it. We're not integrating with respect to negative infinity to positive infinity. That's nonsense. That'd be an infinitely long rod, which, shock and awe, the moment of inertia of an infinitely long rod is infinite. Like, not very exciting. That's obviously not this problem. What are the bounds? What is the lower bound and the higher bound? And this is what you're going to integrate with respect to. You have to integrate across the entire rod. Try it. See if you can figure it out. It's a puzzle. Oh, and you know the final answer. So if you've got some idea of bounds, you know the final answer is going to be 7 over 36 ml squared. So if you really want, you can try your bounds out and see if you get the right answer. But don't feel rushed. Okay, do you want some idea of bounds?
Hey, I got it.
Okay. So basically our bounds are going to be the leftmost point and the rightmost point. That's kind of what we got to integrate the whole part. Positive or negative? That's your lower bound. And what's your upper bound? There you go. And in that way you integrate the whole thing. Yeah, but the negative L over 6 is really important. And it's really easy to prove why. If you said it was positive L over 6, you'd instead be saying that your rod, which is fine. You could find the moment of inertia of a rod that is rotating about that's fine, but it's just not this problem. Yeah, it would even be its own unique rod. It would be like the rod, the left part of the rod being cut off, basically. So that's just how you do any one-dimensional. If it's three-dimensional, we would just do this. So it's really just we got to integrate over the whole thing. So it's the leftmost point and then take the right. That's the bound. So what is the leftmost point? That's a good question. Yeah. So where's our zero? Where's our origin? What are we measuring with this? So I'm just gonna. The axis is our 0 because this is all ours. How far away you want? So this is my 0. So the question is, where is this located? Let's say. And then that's your left bound, and your right bound. And then integrate. All right. So the question is, where is the left? We got to integrate over the whole bar. So you choose the left. The leftmost point is my lower bound, and my rightmost point is my upper bound, and that way I integrate over the whole bar. That's the whole point. I need to integrate over the whole bar. So the lower bound is the leftmost point. The rightmost point is the upper bound. Now, this is where you all got to be careful. You got to decide, where's my 0? Where is everything being measured with respect to? The axis is my 0. So my leftmost bound, give you all 10 seconds if you haven't thought about it yet. Take your guess in your head. The leftmost bound, y'all, is negative L over 6. If you put it as positive L over 6, instead you are pretending that your rod starts here. Positive L over 6 is to the right. If you don't do the positive, you're saying your leftmost bound is here, which obviously it's not. It's on this left side. And then our rightmost bound is going to be, hopefully, with that in mind, give you all 10 seconds, see if you can figure out the rightmost bound. It's going to be 5L over 6. And ta-da! I integrate over the whole bar. I integrate from negative L over 6 to positive 5L over 6, which ends up being the whole L, the whole length of the rod. Again, if you put this as positive L over 6, you're finding the moment of inertia of this rod. A rod that's rotating. It's not the full rod in that case. It's a different problem that you're solving. So your integral needs to match the problem. You need to integrate over the entire rod. Go ahead and do it. Y'all can do this integral. R squared dr, super easy integral. You got your bounds, plug it in. And then there's just one thing I got to show you at the end. There's one thing I got to show you at the end, and you might discover this for yourself. Remember the answer, you all know the answer. We literally found it. We did it in the last problem. This is the exact same problem, just a different way of solving it. So, try it out. You can integrate this. I believe in you. Yeah, but what's cool? If you multiply lambda times L, what does that give you? What does that term turn into? Lambda times L. The density times the length. Ta-da! And that's where our math spits out again. Yeah. And so if we had an object that was three-dimensional, we'd integrate not only this. So like if instead of this problem, instead of it being a thin rod, if I made it like a rectangle, I would also integrate vertically. No, I'm actually vertically, I guess. Now would you? If you made this thin rod and you made it a plank, it wouldn't matter. Unless that plank had a thickness that also rotated. That would actually be terrible. So it would be really unpleasant. Yeah. I'm trying to think of what we
No way.
I would pick an easier example. We're doing a double integral. I'd probably do a cylinder with some thickness, but I do it like spinning this way. So funny enough, I think. Okay. Yeah, this one would be two-dimensional because you would integrate with cylindrical coordinates with respect to r and with respect to theta.
No. Oh, what the hell are you talking about? Sorry. Oh, because I didn't.
Did it work?
No, you don't know how to do that.
So it's density. Yeah, so if you remember the OG density from yeah. So in this case though, it's a volume. It's just a line. So volume turns into length. Yeah, you got an extra L. You're like, what do I do with it? But you're also missing the mass. But if you multiply lambda times L, by what? Yeah, it's up the mass. There, gotta go. Sure. Yeah, looks good. I recommend just pulling off that. Yeah, the integration is going to be, or the 1 over 6 cubed. You're on the right side. Alright, did y'all figure out the integral? So definitely has to turn into 7 over 36. The 63 divided by 7. Hey, 324 divided by 7. Oh, sorry, actually, that's the right question. 63 divided by 7. 324 divided by 30. So that is 7 over 36. That simplifies to 7 over 36. We did it. We do, and this is where, what is lambda, what the heck does that variable stand for? It is mass over length. Yeah, no, that's perfect, that's good, that's the reason to write things down. It's density, it's mass over length. So if we multiply it by 1, you should have L to the third. So you should have L to the third. Yeah. So if you multiply that lambda times L, if lambda equals mass over L, if you multiply lambda times L, what does it give you? No, lambda times L. Yeah. Turns into mass, so you get 736 mass. Got rid of an L. So elsewhere. So it's L cubed, but when you multiply lambda times one of those L's, it turns into not times mass. So that's how we get our mass back, because the answer is 736 and L squared. Yeah, so we get our mass back. All right, so let's actually do this because I want to show you all the last thing as well. So we integrate this, so we get lambda r cubed over 3 evaluated from negative L over 6 to positive 5L over 6. We're just going to pull out that third because I don't want to deal with it right now. So we get 5, 6 cubed minus plus L over 6 cubed. Because it'll be to the third, so you get a negative out, so works out. If you want, here, I'll put this here so people aren't like confused. There you go. Oh, did I do the wrong?
No, you just.
Oh, thank you. Yeah, that's gonna. I don't know if I would have caught that later. All right, so we get lambda over 3 times 125 L cubed over, gosh, what's 6 cubed? 36 times 6. 216 minus 1 over 216 plus, thank you. It's really funny that that bottom term like barely does anything to it, but it does. And if you do all the things, so we get lambda times, so gosh, what is that? 126 over 216 times 3. What the heck is that? Oh, yeah, we could also divide 126 by 3. Let's do that. Nah, that's going to confuse people. I don't know. What's 126? Where's my calculator? Anyone know what that is off the top of their head? What is it?
42.
42. 42 over 216 lambda L cubed. And then if you simplify, 42 is divisible by 6 and 7, 216. Long story short, this does turn into 7 over 36. You can prove that to yourself if you want. That's the least common denominator. And you look at this and you say, yep, that's totally the same thing as 7/3. Do these look the same currently? No. There is one last step. And this is kind of where the cool thing where I said, don't worry about lambda. Reminder to you all, what the heck is lambda? It's density. It's linear density. Lambda is my mass over my length. Just like normal density is mass over volume. So, 7 over 36. If I just take one of those L's, I say, I'm just going to borrow that real quick. Lambda times L is mass. Lambda times L is mass based on the definition. Lambda times L equals mass. And so this is the last kind of cool thing that pops up. You're like, oh, we didn't have density. No, we didn't. But it turns into mass. And we get the same answer. And now I've hopefully convinced you why the parallel axis theorem is much nicer to work with. You can either do this integral or just add md squared to the one around the center.
Did you multiply the 1 over 3?
Yes. I did 126 divided by 3. So I did 125 plus 1, and then I divided that by 3, and it turned out to 42. Yeah. All right. So there you go, y'all. This is how you find moment of inertia, the brute force, not the brute force way, the equation way. I don't know what you want to call this. The definition. This is the definition of moment of inertia, the integral. It's a one-dimensional case. If I gave you all an object, I can't give you all really many cases of this because most objects are three-dimensional and you'd have to integrate. And you'd have to know about spherical coordinates and cylindrical coordinates, and you haven't bothered with those yet, very likely.
They're fun. They're really fun.
They're really nice.
Jacobians too.
Yeah, Jacobi. I don't remember Jacobi.
It's just
Whatever
your
substitution.
Oh.
Like,
Like,
Oh, yeah. That thing chucked in to make it work.
yeah.
Yeah, I don't remember being called a Jacobian, but I'll trust on that. All right. Cool. We did it. Yay. Great. What was the point?
Oh, what was it?
Why did we even do this? Why did we find moment of inertia? Because everywhere where mass shows up in a linear equation, we're going to replace it with I. For example, kinetic energy is 1/2 mv squared. So what's the one for rotation going to be? Replace M with I, replace V with W. Ta-da! Everywhere mass shows up, we're going to replace it with an I. Every single equation that I've given you all with mass gets replaced with an I. Kinetic energy was one of those equations. F equals ma was another equation. We're going to replace F with torque. We're going to replace M with I, and we're going to replace alpha, or A with alpha. Ta-da! Look, it's Newton's second law for rotation. And the last equation I gave you all with mass was momentum. P equals mv. We're going to replace P with angular momentum. We're going to replace M with I. Everywhere M shows up, it gets replaced with an I. And this is why we needed I. And this is the most complicated part that I had to teach you all. Moment of inertia is the most complicated thing. Everything else is what you've already learned just from the new paint job. But teaching you how to figure out what the heck I is, that was kind of the new thing. That was kind of the only brand new thing of doing the integral of r squared dm. So, there you go. We're not going to really get to angular momentum, sadly, but I will definitely do rotational kinetic energy and torque. And that'll be the last two things I need to teach you all. How to find angular acceleration based on torque, and how to find, including rotational kinetic energy in your all's conservation of energy equations. So, there you go. If you all were good with conservation of energy, great. It's more the same. Now you just got a new energy term. If y'all were good with F equals ma, great. Same logic, but with that. All right. You're going to hate this. Which will reach the ground first? A 5 kilogram block sliding frictionless down a ramp, or a 5 kilogram sphere rolling without slipping down the same ramp? I'll tell you all, the sphere, there's friction involved. You can't roll without friction. You all saw that last lap. Things don't roll if there's no friction. Hydroplaning and all that jazz. I'm just foreshadowing the future. Okay. We really don't have that much, y'all. We got like 10 more slides. Yeah, the last one we're going to do today is one where I actually didn't realize I was doing it wrong until 5 days ago. Something when another instructor using my stuff realized I'd mistaken. And ChatGPT also makes the same mistake when you plug in the problem. So it makes me feel slightly validated.
I have access to those sites.
Mm-hmm. Yeah, try it out. See if you can avoid the mistake that I made. It's very, yeah, if you do, kudos. But I can, yeah. Alright. 10 more like 5 more seconds. I mean, at this point, just guess. 3, 2, 1. Alright. So, you all learned this from last lab, kind of, sort of, that when things rotate, there's an energy associated with it, and it steals some of the linear motion. It steals some of the energy. So if we set up this equation, you remember, y'all, the classic, energy initial plus work equals energy final. The bread and butter of all energy problems ever. Both of these start with the same energy. Both of these start with potential, the same exact potential. In the first case, there is no friction, so there's no work being done. In the second case, there is friction, but there is still no work being done. When something rolls, it doesn't lose any energy to friction unless it slips. If something's, there's a reason we like wheels. The real world has friction. Like, that is reality. And the beautiful thing with a rolling object is friction isn't affecting it unless the object is slipping. So, anywho, no work done in either of these cases. No work, because friction is not, it's not, first case, no friction, second case, rolling without slipping. All right, what energies do they end with? The first object only ends with kinetic. The second object also gets this term. It's also moving, but it's got to share. The second object has to share some of that energy. It loses some of it to rolling. And this is where I told you all, like, remember the last question, which object would roll down the slowest? It's the one with the biggest moment of inertia. Long story short, a block is going to reach the bottom first. And the reality is, look, y'all, if there's no friction, that's always going to win. Like,
Yeah.
at the end of the day, no friction is the most ideal situation. If there was no friction, the sphere would not roll. The sphere and the block would reach the bottom at the exact same time. If you put a sphere on a surface with no friction, it will not roll. It will just slide down it. The only reason things roll is because of friction. I mean, yeah, again, case in point, if you're on ice and you hit the gas in your tire, yeah, your tire is going to spin. You're not going to go really anywhere unless there is enough friction. I don't know. Maybe you get lucky and you get enough friction, you get off the ice. But that's why ice is dangerous. When you run over an ice patch, you lose control because friction is useless to you. Your tires turn because of friction. Without friction, your tires don't do jack squat. You're at the mercy. Yeah, have you all ever seen those videos of like an icy hill and all the cars are just sliding down it and they're frantically trying to rotate? Yeah, they're all on a frictionless surface and they're all suffering the consequences. What can you do? I mean, friction is the reason you can interact with the floor. If there was no friction in life, it's not actually a good thing. You're like, man, if only the world was friction. If there was no friction, you couldn't go anywhere. The only way you could travel if there's no friction is by throwing objects the other direction as you, i.e. you're in space. How do you move in space? You have to have a rocket to shoot something out the other direction. You have to lose stuff, and eventually if you run out of stuff, you're stuck. So, that sucks. All right, great. There it is. I showed you all this term last time. Now you've seen it again. Rotational kinetic energy is just like translational. You just do the swap. M becomes I. V becomes omega. Really, really straightforward. Really nice and easy. And now you all have 4 energies to consider when doing conservation of energy. Potential due to gravity, potential due to spring, kinetic due to linear, and kinetic due to rotation. 2 types of potential, 2 types of kinetic. And that's the checklist for you all. When you get to physics 2, you'll have another one.
I'm so glad I don't have to deal with ice in Florida. It sucks.
Yeah, I've never experienced it and I don't want to.
It's driving is so scary.
Yeah.
In America, like this.
All right. I'll leave that up for 5 more seconds. In case anyone... Go! All right. 2 spheres with the same mass are rotating at the same angular velocity. If sphere 1 has half the radius of sphere 2, how do their rotational kinetic energies compare? So this is one of those questions where I say I change something. How does something else change? Remember the trick. Write down the equation for the thing you want. What is the thing you want? It's rotational kinetic energy. What equation relates rotational kinetic energy to the things that we have? Let's see how this goes. Yeah, this one might be tricky to do in your head. Maybe you can figure it out. Write it out. Write out the equation. See what changes in the equation. Make that change. Pull that change out. Rotational kinetic energy. What's the equation for that one?
If it's anything.
What's regular kinetic energy? If you remember the translation one, you remember what's wrong. So then go from there. What's changed in the problem? Where is that going to show up? Yeah, it's okay. You got your rotational equation. So we're taking out this. What variable is G? And where did that show up? So then we can kind of replace moment of inertia, so we actually have R, and then just make the change. Oh, no, yeah, so that's, should sphere 1 have a higher rotational energy or a lower rotational energy? Or R? And that's always, yeah, you can always go back and check that. If it has half the radius, R goes down. R goes down. Yeah. All right, y'all, remember, the way to always do these problems, you can try to do it in your head, but if you haven't realized this one, man, this is maybe a little hard to do in your head. You start with the equation that relates what the heck do we care about? Rotational kinetic energy. There's literally only one equation with kinetic rotational energy. 1/2 I omega squared. And you look at that and say, what variable is changing in my problem? So like, we're trying to compare kinetic energies. Great. I solve for kinetic rotational energy. I don't have to rearrange it. What variable is changing? Indirectly, it'll be I. Which is the one it directly says is changing? The radius. Where does the radius show up in here? An I. So we rewrite this. You write the thing you want in terms of the things that change. That's how you do these. No matter what type of problem I give you, I could tell you the mass triples and the radius halves and the angular velocity quadruples, and you can do this. You just write it in terms of all the things that change. And you go from there. So I'll give you like 30 more seconds with that. See if y'all can figure it out. You got to write the relationship between the two objects as well. How do the R's compare? Yeah, and it's really easy to just think through logic. What makes sense? If sphere 1 is half the radius, should I have more energy or less energy based on that equation? If I have half the radius, should I have more energy or less energy? So then your answer should not check. Yep, that's always the last check. Does it make sense? And then check if your answer makes sense. If I have half the radius, should I have more energy or less energy? You should always do that last kind of intuitive check based on this. You can always go back and kind of do that. All right, give you all 10 more seconds. If you're not sure, make a guess, and then I'll show the magic.
So it makes sense. Yeah.
All right, in 5, 4, 3, 2, 1, stop. All right, I want R1 in terms of R2. Sorry, I want kinetic energy of 1 in terms of 2. So I'm going to write these. R1 is half of R2. I'm going to write that relationship somewhere because that's what I'm going to substitute in. So this here, we could say that this is the energy due to object 2. Great. It's the mass of 2 times the radius of 2 times the angular velocity of 2. Fantastic. And then we could do the same thing for 1, for object 1, is 1/2 times 2/5 times m1 R1 squared times omega 1 squared. Here's the thing. Omega is the same, so I don't really need to define that. M is the same, so I don't really need to distinguish those. So it's just the radiuses that are different. And then all I'm going to do is put in how they're different. So I'm going to replace R1 with 1 over R2. And then you just pull out the number that changed. You just pull out the number that changed. There's a 1/2 in there that gets squared. So when you square that, you get 1/4 and you just pull that to the front. Do not pull any other numbers to the front. Only pull the number that changed. Only pull the number that changed. Everything else better stay in there. If you do not keep everything else in there, you're going to get awful things. R2 squared. And behold, this is this. So like I'm kind of writing it out more and more in detail, but literally all you do, find the thing you want to find. So in this case, it's kinetic energy. Find what changes, make the expression in terms of those changes, and then just pull out all the numbers. Pull out all the numbers. So like in this case, if I said the mass doubled, the radius was 1/2, and the angular velocity was 4 times, I would just put those numbers in front of everything, pull them all out to the front, and that would give me how they changed. It's really simple, really straightforward, and this works for any problem like this. If this changes, what happens? And really useful skill. It's a really useful skill to be able to look at an equation and say, if I double this, half this, triple this, what's going to change? I would generally just a multiplication problem. If there's plus signs, it's a little bit less pleasant. But there you go. And it makes sense. As radius goes down, kinetic energy goes down. Rotational kinetic energy goes down. All right. Yeah, this one's good. A neutron star, which is like the most dense, other than a black hole. It's the most dense object in the universe. I mean, look at that mass, y'all. It has 1,000,000 times the mass of Earth, but it only has a radius of 10 kilometers. Like, that's wild. And they got crazy energy. And in form of rotation. Find it. And period here is the time it takes for one. Period here is the time it takes for one full revolution. If you plug in this period as angular velocity, it's wrong. What?
Equal to
Two objects separate. Are they separated at the end, or
they're together.
they're together both cases? Yeah. So you just
Because at the beginning he's on it, and the thing is spinning.
Yep. So it's just the carousel. Yep. And at the end, it's two objects. It's kind of like something getting stuck to the wall. If you really want, you can do like it'll be I times omega final, and it's the exact same omega because they're stuck together.
Because the eye of a rotation.
Yep, and then the omegas are the same. So basically, this is like two objects. It's an inelastic collision. This is an inelastic collision, but for rotation.
Yeah, that's what I was thinking. Over.
All right, so you write down your givens. Mass is 2e30 kilograms. The radius is 10e3 meters. If you didn't convert it, then you're going to get a wrong answer. And period is 0.02 seconds. You all got to do something with that period. I believe in you. Basically, this question is, do you know what the heck angular velocity is? Can you get there? I believe in you.
I would think it'd be this. Yeah. Factoring this out.
Yeah. I'm just going to trust that's right. I mean, like, the previous logic was good, so I assume.
Yeah, it's just an addition of both.
Yeah, and it's literally a inelastic collision. It's the exact same process for an inelastic collision linearly.
Mm-hmm. Because this is added to the boy's initial, but he's standing still. What are we going to do for the final? This one?
The pulley.
The pulley?
Yeah. So we're not going to do anything with angular momentum.
This one right here?
Yeah.
Okay. I can try to do it.
Yeah.